So today we're moving on, and we are going to talk about what happens when you add or subtract a constant from that function f of x equals ax squared. So as you can see here, when c is greater than 0, the graph of f of x of ax squared plus c is a vertical translation c units up from the graph. So that's going to be, grab a different color and I can highlight that for you. All right. That is when c is larger than 0, it goes up. Then when c is less than 0, the graph is a vertical translation. The absolute value of c units down. So that's this one here. And I just want to point out these graphs here look like maybe that red one is a little bit wider. Maybe it might be more of a vertical stretch, but just know that there's no stretch or shrink in these when you add that constant. So the vertex of the graph is going to be 0, c. Okay, so wherever that c value is going to be your y value, but it's still going to stay here at x equals 0. And what I want you to write down, and we're going to talk about this a little bit later, but what I want you to write down is that this function is going to be used in free fall problems. They're going to call them the free fall problems, or you're going to see a problem in the book where something is falling, and you're going to use this function. F of t equals negative 16 t squared plus h. So this function here is what you need to have in your function toolbox for problems where you see there's a free fall. And that h is the initial height in feet. And I'm going to go over a problem like that in a little bit, so that'll make more sense when we get to it. I want you to just go ahead and write that down to start off with. That way you kind of remember that we talked about it before, and it might pop up in your brain a little bit when we get to it later. So we're going to move on to number 1, and we're going to graph the function, and we're going to compare that graph back to our good old original parent function of f of x squared, or f of x equals x squared, sorry. So we'll start with graphing that parent function, and we're going to do that in green. And I don't need to go and tell you what everything equals because we've done a lot of those recently, right? So many parent functions, we know exactly what we're graphing here. We're going to make these 1-to-1 ratios. There. And I know that my points are not really visible. It's hard to make them super visible without getting way off track. Now, our new graph is g of x equals x squared plus 5. What we're going to do with that is move that up 5. Because if we go back and we look up top, it says when c is greater than 0, so this is our c value right here. Let me make that blue for you. This is our C value right here. It's greater than 0, so it is a vertical translation C units, in this case 5 units up from the graph. So we go 1, 2, 3, 4, 5. That's right here. That is our new vertex. Our vertex is now 0, 5. And then we basically have the same thing. Okay, so it would be right there, there. And you can plug that into your table to get those exact points. So it looks like it's getting skinnier, but that's just because my graph is not finished. The opening is actually exactly the same. All we've done is shift that up 5 units. On number 2, we have x squared minus 3. So we're still going to be opening that up. I'm going to make my axis about right there. Because if I start with 0, 0 on my parent function, let me go back and make that parent function green so that it looks the same as the other one. We have a green parent function. But what this is telling us is that C is less than 0. That's a negative 3. So that is going to go, that's a vertical translation. It's going to go down the absolute value of C, which is 3 units. So we're going to go 1, 2, 3. Let's change colors one more time. Our new vertex, 1, 2, 3, is about right there, which is going to look more like that. Vertex is still 0, and then a negative 3. So all that's going to do when you add or subtract that constant is move your graph up or down. So far, we're not going left or right or anywhere else off of that y-axis right now. It's just going to go up or down. I'm going to go ahead and pause this right here. You guys go ahead and pause this, do these graphs, and come back and check your answers. So if you've done these correctly, again, my parent functions are in blue. On number 3, I moved down 2, so that is a vertical translation going down 2. And right here we have a negative, so that means it's going to open the other direction. And covered that up, so we have a negative with a vertical stretch with a factor of 3. So my green one is facing down, it's a little bit skinnier, and it's moved, its vertex is there at 0, negative 2. It has a vertical stretch, a factor of 3, and because it's negative, it's going to open down. Going over to number 4, we can see that there's no negative, so they open the same direction. We have a vertical compression with a factor of 1/2. And our vertex is at 0, negative 4. All right, number 5. This should be pretty familiar to everybody. We are going to find the X-Intercepts which is the same thing as finding the zeros. So that means when we're finding the zeros, we are looking for when y equals 0. We want to know when that graph is crossing the x-axis. So the first thing we're going to do is set that equal to 0. And if we didn't say it enough times in the last unit, we are going to check for our GCF. In this case, there is a GCF of -1. And I can tell here that gives me a difference of squares. And as you can see, this is one of the reasons that you really have to remember those patterns, because everything we learned last unit is going to really come full circle here. It's going to help us know everything that we've done. We're going to put it all together, and we're going to find those x-intercepts, which are x plus 1 equals 0 and x minus 1 equals 0. Take away 1 on both sides here. We get x is -1. Add a 1 on both sides here. We get x is a 1. And our x-intercepts are -1 and 1. Again, we're looking for when y equals 0. So we're going to start with setting this equal to 0. I'm going to go ahead and pull that GCF. And I'm going to pull a -4, which is going to give me x squared. Oh, yes, x squared minus 4. I see once again that I have a difference of squares, but there's another way you can solve this, which is sort of what I told you last time. You can take that and you can set x squared minus 4 equal to 0. Move that 4 over, add 4 to both sides. So you have x squared equals 4. And then you can take the square root of both sides, which is 2. But we're not done there because it's going to be a plus or minus 2. So those are the two ways you can solve those. It's very important, though, when you take that square root, that you remember to put that plus or minus 2, because when you graph that, you'll see that it crosses both at x equals plus 2 and x equals minus 2. So you can't forget that plus or minus 2. We're going to skip 7 and 8 and move on to number 9. Take a look at that. We're going to sketch a parabola with the given characteristics. So the parabola opens down, which we know because that's given to us. We know that's going to have the legs or what have you pointing downwards. And the vertex is 0, 5. I'm going to do this in color just so that it shows up a little bit better. And since we're opening down, I'm going to make my graph go this way. So there's 0, here's 1, 2, 3, 4, 5. Well, that's not going to work. This is why we say it doesn't really matter. I'm sorry. Scratch that. I'm going the wrong direction. We're going to go... We're going to back up a little bit. I read that wrong. I'm sorry about that. I'm going to make my... That's how I'm going to draw it. So I've got 1, 2, 3, 4, 5. 0, 5 is our vertex. And we're going to open that down. I think of a football every time I see that. Maybe you do too now. You're welcome. Okay, let's do number 10 because that way you kind of will get a better idea. The lowest point on the parabola is 0, 4. If the lowest point on the parabola is at 0, 4, it cannot open down because that would say everything underneath that would be lower, right? So we know that 0, 4 is the lowest point on the parabola. So again, 1, 2, 3, 0, 1, 2, 3, 4. So there's 0, 4, and it would have to open up because that is the lowest point on the parabola. All right, let's talk about those free fall problems that I talked about earlier that I said we would be talking about later on. So the function f of t equals negative 16t squared plus s of 0 represents the approximate height in feet of a falling object t seconds after it is dropped from an initial height. That's that s of 0 in feet. A tennis ball falls from a height of 400 feet. So in this part A, what it's telling us is that the initial height is 400 feet. So if that equals 400, we can plug that right into our function and say f of t equals negative 16t squared plus 400. All we did was take that 400 and plug it in right there. Well, if it's going to hit the ground from 400 feet up, we know that that needs to equal 0. I thought it said equal to 0. First thing we're going to do is pull that GCF, which is going to be negative 16 in this case. That's going to give us a t squared minus 25. And I'm going to go ahead and I'm going to do that with the square root method to solve. Set that equal to 0. Move that 25 over. Which is going to give me t squared equals 25. Taking the square roots of both sides, I will get t equals plus or minus 5. However, with this problem, we know that it's a time problem, and we can't have negative 5 seconds, so our answer is 5 seconds. When we move to B, it says, suppose the initial height is decreased by 384 feet. After how many seconds does the ball hit the ground? Well, our initial height was 400, but now we're going to decrease that by 384. So 400 minus 384 gives us 16. It is only falling 16 feet this time. So our initial height is 16, and we're going to go ahead and plug that into our formula. Set it equal to 0. And we should be able to see right off the bat that we definitely have a GCF of negative 16. And let's go ahead and do that with our difference of squares this time. So I have a t plus 1 and a t minus 1. I'm going to set both of those equal to 0. T equals negative 1. Or t equals 1. Again, this is a time problem. We know that one doesn't make sense. There's our answer. So it would take 1 second. Those should look pretty similar to what we did last unit. It was just mostly recognizing this function up here for that free fall formula where you have to find in your problem there what that initial height is. Let's do one of these together, and then we'll just do the rest in class tomorrow. So let's go ahead and do number 12. Now, I see that I've got f of x equals 3x squared plus 4, and then I have g of x equals fx plus 4. Well, I can go ahead and I can plug that f of x in to that g of x function and just get one function to graph. So what I'm going to do is I'm going to take this function and I'm going to put it right in there. So let's rewrite that. We have g of x equals 3x squared plus 4. There's our f of x. And then we have to add 4 to that as well. Combine like terms, we get 3x squared plus 8. Looks like a pretty easy graph to graph, easy function to graph. And if we make this our y-axis, axis here, we know that that has to move up 8. So I'm going to count by 2. Okay, that's 2, 4, 6, 8. All right, so our vertex for the 3x squared plus 8 we know is 0, 8. Then if we have 2, 4, 6, 8 here, negative 2, negative 4, negative 6, negative 8 here, it's going to be 11, and then 4 will be 20, so it's going to be 4 way up here. That. And that's going to be that. Whoops, sorry guys. Let me redo that a little bit. So if I went to, that's going to be what we just came up with, the 3x squared plus 8. But if I want to look at it in relation to just f of x, g of x is our green graph. I'm going to go ahead and I'm going to go back and I'm going to graph that f of x plus 4. Well, I know I'm moving up 4, so that's going to go right there. 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 Well, I apologize, but my over on this on the left there, they got a little wide. But we can see that just by plugging in our f of x into that g of x function, it's just moved up 4 more. We just added 4 to f of x and shifted it 4 more than the original. If we just had a 3x squared, it would start at 0, 0 and look exactly the same as the other two. So we'll stop there for today. We'll do a few more of these in class tomorrow. Write down any questions you have for me, anything else you might want me to talk about it, and I'll see you then.